Okay, thank you, Drew. Hello, everybody. This is Dan Vega. I'm going to be presenting the FC3 work scope today. I'm the Federal Program Manager for a campaign that we call the Materials Protection, Accounting, and Controls Technologies campaign. And this work scope is administered underneath that campaign. And this year's work scope will kind of be a bit of a subset of the larger MPACT picture. So that's the reason it's called Advanced Process Monitoring for Domestic Nuclear Safeguards, as opposed to the broader campaign. Those of you who have been following us for a few years will notice that the specific work scope changes a bit year to year. Several years ago, we had looked for used fuel security safeguards approaches, and then 2 years ago, we're looking for electrochemical or pyroprocessing safeguards approaches, and last year we were looking for data integration. So this year it's advanced process monitoring for domestic nuclear safeguards. Real quick, I'll just go over MPACT in general, and then I'll cover the work scope for this solicitation. Essentially, MPACT's mission is to develop innovative technologies and analysis tools to enable next-generation nuclear materials management for existing and for future U.S. nuclear fuel cycles, and thereby minimizing and managing proliferation and terrorism risk in the process. For the most part, this involves technology development, better safeguards instrumentation, better equipment, but at least as much so, analysis tools and other ways of doing sensitivity analyses to determine what we get from for an overall material control and accountability standpoint by having better instruments, better analysis tools. Additionally, we're tasked with performing technical assessments to support, fuel cycle concepts as they come about. For those of you who watched the beginning when we discussed GAIN, you'll notice there's plenty of advanced reactor concepts involving more exotic ideas like fission products and fuel, and MPACT would be the place where we try to get a handle on what would be required for a good safeguards approach to such things. And finally, leadership. We work on developing guidelines for safeguards and security by design, which is this overarching theme of doing working on these processes up front and applying them to new facility concepts. We do most of that by releasing what we call roadmaps on specific subject areas. Those are available if you would like to contact me afterwards, but I didn't put them in this presentation because they're not relevant to this year's solicitation per se. So the 5-year high-level milestones, we're kind of in the middle of a 5-year process where MPACT was retooled a little bit, but we have completed these field test plans for new instrumentation technologies, and that these field test plans were doing real work in real facilities like H Canyon. Additionally, we've been working on initiating new instrumentation projects. So these are perhaps high risk, high reward, novel types of detectors that may be revolutionary as opposed to a small evolutionary increase in, say, resolution. Additionally, we've been working aggressively on electrochemical processing, pyroprocessing, and that's to help support other campaigns within fuel cycle, including a demonstration going on in Idaho. And the safeguards and security of extended fuel, used fuel extended storage, which will, in fact, after this fiscal year, be an element that moves out of MPACT and will be more closely linked with the used fuel office, which will be born hopefully in the beginning of next fiscal year. The most important of these high-level milestones to this solicitation is the second to last bullet that you're looking at, which is the development of physics-based time-dependent signatures to guide advanced monitoring technology development. The idea here being that if you have a physics-based understanding, if you know your geometry and you know your chemistry, then what do you expect? What signature do you expect to see in, let's say, a chemical fuel separations process, whether that's a Urex process, a Purex process, a co-extraction of uranium and plutonium, and so that you can compare what you expect to find with what you're actually finding. So it's a difficult combination of physics-based model and advanced instrumentation. And the last bullet there is vulnerability assessments of used fuel. And as I said, we're not going to be looking for that in this year's solicitation. So the more ongoing kind of long-term objectives here are, as I mentioned, the safeguards and security by design paradigm as a way to incorporate safeguards and security into a nuclear energy system from the beginning rather than retrofitting it. So this probably needs to be done in order to license a facility through the Nuclear Regulatory Commission. It's a much harder case to say, well, once we get this built, we'll be able to figure out where the plutonium's going, as opposed to presenting a good case up front. Additionally, to demonstrate these nuclear material technologies and approaches to prove that they work by actually putting them in the field. Let's see, the third one here, to address the issues associated with technology development as it's being developed in other campaigns. If you watch the previous presentations, and I believe it's the FC1 domain, the material recovery and waste form development is working closely with us. In fact, we will be in the same office after the reorganization I mentioned, and MPACT will continue to work closely with that campaign. So as they come up with let's say a denitration process, or you know, some other co-extraction method, or you know, a tritium treatment or things like that, they will be looking to us to support them from a nuclear material accountancy standpoint. Also to support NRC rulemaking through engagement and data generation. The NRC does have some regulations on the books for, you know, a hypothetical reprocessing facility, but they are not quite closely developed enough to bridge the gap between what we can do and what the NRC might require. And so, you know, for instance, what category would a reprocessing facility be based on its material attractiveness, and what requirements would it need to meet based on the Code of Federal Regulations. Most of these, of course, are given in 10 CFR Part 73 and 74 for the physical protection and the safeguarding of nuclear material. And finally, to maintain our position, engage internationally to help influence and support the nuclear energy enterprise and demonstrate U.S. leadership in this field. So I'll go ahead and just give the work scope verbatim, and then I'll give a quick example of what we mean by process monitoring. So the FC3 scope for this year is looking for sensors, techniques, and approaches for integrative advanced process monitoring to enhance nuclear material control and accounting and used nuclear fuel reprocessing facilities. So a place that has chemical separations of nuclear fuel, whether it's partitioning for waste optimization, or for recycling for fast reactors for thermal, but for a reprocessing facility, hypothetical domestic reprocessing facility. So this area includes radiation-based and non-radiation-based approaches, either or both of those, with the goal of providing quantitative analyses to supplement traditional nuclear material control and accounting measures, resulting in improved performance of the safeguard system to meet the NRC requirements. And as I mentioned before, the NRC MCNA requirements given in the Code of Federal Regulations, 10 CFR 73 and 74. I'll give a quick example here of what we mean by kind of combining tools that we already have in order to have an integrated process model. And I by no means am encouraging somebody to do the same work or to emulate it, but this is just an example of what we mean. So it's the correlation of multiple isotopes using gamma spec to enable detection of the process changes. And as I mentioned before, a very complex chemical process is also a very complex process from a radiation field standpoint. And so if you have a pattern recognition with using multivariate data, and you couple it with a process monitoring technique, then you can use kind of the best of both worlds. A hypothetical plant could shut down and take an inventory of all the material, and you probably get a pretty accurate number, but it would be interruptive to the process. Or you can put a rudimentary process monitor in place, let's say something simple like a pH, like a pH detector. And you may be able to tell when conditions are severely off normal, but your accuracy would suffer. And the hope here is that we can combine these in such a way that process monitoring can begin to approach the accuracy of traditional nuclear material accountancy methods. So with that, I'm happy to answer any questions and welcome anybody who wants to follow up via email, phone call to get my contact information from the website. And I'm happy to answer questions.
Would enhanced radiographic methods for quantitative material accountability be of interest?
It's possibly, but what I'm familiar with radiographs, that's you know, to tell the composition of a fuel assembly or something like that. What we're talking about more here is a chemical process, which is dynamic. So we'd be looking for near real-time accountancy. So if radiography can be applied to that in an interesting way, then we would be interested. But a static measurement of, let's say, a fuel assembly, probably not so much.
Dan, is there a particular system that you would like to see technologies developed for?
Well, we're focused here on potential reprocessing systems. As far as detector system, no, I mean, people have used gamma. You can do more isotopics with gamma, but neutron techniques are also valuable for getting total fissile content, things like that, and traditionally optical methods, you know, Raman spectroscopy, UV vis, Hyrex, those types of non-radiation signatures, but no, not a specific system other than one that could be applied to a chemical process, chemical separation process.